you very much, David, for the introduction. This is Olivier Guyon. I'm going to start giving the presentation and then hand it over to Josh and Mike. We're all very excited for this opportunity that you are providing us to talk to amateur astronomers for the simple reason that our main audience for this, our main goal for this project is to involve amateur astronomer, citizen scientists, and also schools into the very exciting field of exoplanet discoveries. So without further ado, let's move to slide 2 on the Project PANOPTES overview and goals. I think we already went over this in the introduction. Our goal is to have a worldwide network of small cameras that monitor a large fraction of the sky from multiple locations to detect exoplanet transit. And unlike all previous projects that are doing this already, our goal is to have this project very much driven and run by amateur astronomers and citizen scientists, and also schools. So there is both a scientific and an outreach component to this project that merge together very nicely, as we'll explain. The PANOPTES project is not meant to be very rigidly stuck to a single science goal, and it very much empowers amateur astronomers and citizen scientists and also schools to explore other things once the network is built. So you are in the driving seat, you being the community of amateur astronomers and the community at large, to come up with new ideas, new projects, and test them. So this is also, we think, an exciting scientific adventure that empowers the public to actually do science projects, come up with their own science projects. Slide 3. For just a visual reminder of our primary goal, which is to go after exoplanet transit. We're looking for the occurrence, as shown in this picture, where the planet passes in front of the star. So this is a picture that some of us took for the Venus, the transit of Venus in June last year. We're not going to see it like that if it's an exoplanet passing in front of a star. We're just going to see a small dip in the brightness of the star, and that's what we're after measuring. To keep numbers in mind, a Jupiter-sized planet passing in front of a Sun-like star will dim it by approximately 1%. So getting 1% level photometry, the ability to measure the brightness of stars to about 1%, is the minimum requirement to start measuring and detecting exoplanets. Slide 4. When we're thinking about a survey, a whole sky or nearly whole sky survey of this type, we need to monitor a very large number of stars with good sensitivity. And the metric, the number that tells us how well we're doing, is what we call Etendue. It's basically the product of our total collecting area multiplied by field of view. And so there's a simple equation here that we wrote. You can write it as the number of units we have multiplied by the collecting area for each unit, each camera, for example, multiplied by the field of view of each camera. And the name of the game here is to maximize the Etendue. And PANOPTES uses a very low-cost available technology to do that very efficiently. So we use DSLR cameras with wide field, actually intermediate field lenses. So our baseline is to use an 85mm f1.4 lens. As Josh will describe, when describing the baseline, that brings us at an Etendue of about 0.2 of a square meter per $1,000 in hardware. So the hardware is not very expensive, but it's actually getting quite a bit of field of view and sensitivity. And if we compare this on slide 5 with other major astronomical projects, and here we have listed the LSST, which is an 8.4 meter diameter telescope currently under construction with a 3.5-degree field of view, we find that actually we're very efficient in terms of covering large fraction of the sky with decent sensitivity. And this basically illustrates that most of the very heavy spending in astronomy is going after very high sensitivity over much smaller field of view than what amateur astronomers can do with reasonably cheap hardware. And so amateur astronomers have a very unique role that they can play for this particular science in monitoring efficiently large parts of the sky. So if we compare the cost per Etendue between PANOPTES and LSST, we find out that we're actually 340 times more efficient than a project like LSST. Of course, for most scientific investigations, LSST is much better than PANOPTES. But for monitoring a very large number of stars, the type of hardware that we're advocating for is actually very high performance. And there's another comparison with amateur astronomy hardware, which is intermediate field of view. So here a Celestron 14 with a hyperstar wide field corrector and a 27 millimeter CCD and a dome would be actually better than LSST at monitoring a large piece of the field of view, but still about 20 times less efficient than PANOPTES. So we're really gearing towards the low-cost but very wide field of view monitoring of the sky, which is not properly covered by current other astronomical projects. Slide 6. So what we really want to do is establish a network, a distributed network of such DSLR-based units that are run by amateur astronomers, not only because it makes sense on the outreach and public involvement point of view, but as I showed you the previous slide, because it really makes sense scientifically. And having lots and small units is a very efficient way to carry out this type of survey. Geographical coverage is also very good, both to mitigate weather, to have continuity in time, but also to cover a large fraction of the sky. And so we really think that for this particular very ambitious type of all-sky survey for exoplanet discovery, amateur astronomers are well positioned to play a key role. And we also hope to involve citizen scientists and schools into joining this network and actively participating in it. So the challenges we have to solve, what keeps us busy, is how to build such a network and how to make it easy for people to actually build such units and join them in a network. Slide 7. Our approach to this survey is to have the whole project essentially driven and pushed forward by the community, by amateur astronomers and motivated citizen scientists, with no boundaries as to who can participate. So everything is open source, open hardware. We are structuring the project from the start in a way that facilitates contribution by anyone. And this is very much driven by the public, and there is no such thing as a rigid boundary for membership. Anyone can participate. So our goal is to really make it easy for anyone to jump in. Slide 8 gives us a little bit of history behind the project. We started in 2010. A few of us, as I'm sure many of you, were doing astrophotography with DSLRs and started to notice that those cameras are a very interesting trade-off between cost and performance. And we did some more analysis of the quantitative analysis of the cameras and found that they are potentially suitable for exoplanet transit. In December 2010, we actually deployed the first prototype with one robotic unit with one camera at the Mauna Loa Observatory in Hawaii, and we started robotic operation a couple of months later of that unit. Since then, that unit has been upgraded a couple of times, and it is now consisting of 4 cameras on the same mount. We're trying different lenses. We tried also to remove the infrared filter versus keeping the camera untouched. And so we're basically, over the last 2.5 years, 3 years, we've basically been exploring the technical feasibility of such a network with this prototype. And what we are doing right now, which Josh will talk about, is we are working on establishing what we call our baseline, which is an assembly instruction set of how to build a unit that is reliable, yet low cost and high performance as easily as possible. And this is something that we need to do to facilitate involvement by public and schools and amateur astronomers. Slide 9 shows our very first prototype, which was deployed in late 2010 on Mauna Loa. And what you can see is on the left, there's a large white barrel for weather protection. Inside it, there is a mount and a camera attached at the end of the mount. The white paste that you can see is weather sealing, so that when it rains on the system, the electronics don't get wet. And the camera is pointing down in this picture because it's in sort of safe mode position, the position it assumes during daytime or during bad weather. You can see there's no dome, and this is a choice we made to simplify the system and to reduce cost. And we'll talk a little bit more about that. And on the right, you can see our electronics. This is the very first prototype, so the electronics is a little bit messy, put together from things that we had lying around in our garage, essentially, and additional things we bought for the system, but not really having yet in mind something that's very standardized and clean and easy to duplicate. Slide 10 shows an image, an example, a single frame of a few minute exposure with no processing taken by this unit. And the first thing we see is that the image quality is actually pretty good. There are a lot of stars in this single image. If you go to slide 11, this is a zoom of the lower left corner of the full field image. And you can see that even in the corner of the field of view, the image quality is quite good. And in a single image, there are about 100,000 stars. So this type of setup is extremely efficient at monitoring a large number of stars. Next slide, slide 12. This is a bit of a quiz. When you build something that robotically images the sky with a wide field of view, there are a lot of things you pick up that are somewhat surprising. One of them is shown in this particular image. You can see two roughly vertical lines, which are satellites. And you can see this diagonal line with the haze surrounded it, which actually is a meteorite that deposited a trail of sodium atoms in the atmosphere that are then dragged by the wind and glow in this image. So this image is actually a difference between two consecutive frames. The reason we show this is to also illustrate that there's a lot of projects that you can think of once you build a robotic network of cameras like that you could run. You could follow a comet. You could try to process the images in a different way to do statistics on micrometeorites. Anything you can think of. Slide 13 shows another image. This time we actually co-added several frames with this first prototype, and you can see that the other thing that this type of hardware is very good at doing is pretty images, which we think is quite important also for outreach. And because the detector is color, we don't have to do any fancy processing. The images come out already quite nice right out of the camera. And if you go to the next slide, slide 14, we basically zoom into one part of the image, showing that there are a lot of features in this image. We can see a globular cluster, a lot of dust lanes. So this is a field right next to Antares in Scorpius. Slide 15. If we think about what we've learned with this first prototype, there's a picture of it here just after a snowstorm. The first thing we learned is that we actually demonstrated that you can run a robotic DSLR system without a dome, and it's quite reliable and durable. So this system ran for about 2 years until we upgraded it. And it survived quite well several storms, and the hardware never the camera never failed. It's actually still running. That camera is part of our prototype number 3, and we're still using the same mount. What we learned a lot of things that we need to improve also. Peeling cables is quite important. We had a couple of issues with that. Planning for long power outage is something we hadn't done, and so this basically builds up a list of things we need to keep in mind so that the final baseline is taking advantage of all those lessons we've learned. The next slide, slide 16, goes into really what is at the core of the feasibility of this network is, can we do photometry? Can we measure the brightness of stars with DSLR cameras, at least at the percent level? And so we actually developed software to do that, to demonstrate that we could do that. The challenge is that if you want to monitor a large number of stars, you don't want to defocus the image. And so and the PSF, the image of a star, is going to be very small, maybe a few pixels, 1 to 4 pixels. As this image moves across different pixels, you get very large modulation in flux. If you just count how many counts you have on what the value of the pixel is. So you have about 20% modulation from one frame to the next, just because the image of the star moves between pixels, which themselves have different color sensitivity. The next slide shows a demonstration of this that we performed this on a star that's approximately magnitude 9.5. So this is so slide 17 shows the full frame image. There's a little green circle showing where the star that we use for this test is. If we zoom in, next slide, slide 18, we can see that star starting to appear in a portion of the previous image. And if we zoom in even more, so slide 19, we can actually see that the star is small. The image of star is only a few pixels, and we can start to see the individual pixels popping up, and we can start to see that they have different sensitivities depending on their color. So 1 pixel out of 4 in this image is sensitive to blue, 1 pixel out of 4 to red, and half of the pixels are sensitive to green. And we can see that in that image. So the next slide, slide 20, shows a sequence of images zooming in on that star, and it's moving across pixels. So the morphology of the image changes, but more importantly, slide 21 shows that if we just measure how much total light we gather in those pixels, and we show this as a function of frame number, each frame being approximately 1 minute, we can see huge variations at the sort of 20% level. So what this tells us is just measuring the total amount of light in a pixel will not work very well. So we developed an algorithm, which is described on slide 22. The first thing we noticed is that there are a lot of stars in this image. So whatever happens to that star for which we want to do the photometry, the same combination of things must happen to at least another star in the image. So the first thing we do is we look for other stars which experience the same defects, and we look for stars for which the morphology of the image on all the frames is the same. And then we use a combination of those stars as a reference against which we compare our target. And these two images shown on slide 22 show that this actually works very well at figuring out the interaction between the image and the pixels. The image on the left is an actual image of our target. The image on the right is what we reconstructed from the reference stars, what we guess that image should be if we removed it from the data set. And we can see that the two images look very, very similar. So that reconstruction is working quite well. And when slide 23 shows that when we apply this algorithm on the same data set, we suddenly get into a very interesting regime where we have, on a time scale, if we integrate over the duration of a transit, with a single camera, we are at or below 1% photometry level. And here you can see the sequence of images. For each of them, we measure the flux, and the distribution of flux is depending on the color, is around 2 to 3%. If you combine the three colors together, it's better than 2%, and that's just in 1 minute. So we have reached a sensitivity that demonstrates that we can calibrate quite well pixel effects, and also reach a sensitivity where we can actually look for transits around other stars. So the slide 24 shows the prototype number 2. We changed two things. The first one is we went to a sturdier mount. So now we're actually mounting on metal frame instead of the wooden panel on the side of a building. And we also put two cameras in the system. We wanted to test if we would gain a lot by removing the infrared blocking filter inside the camera. And what we found is that it doesn't make a huge difference. So for the baseline, at least, we will not advise people to take apart their camera and remove the filter. The camera, as you buy it, is perfectly good for this type of work. The next slide, slide 25, shows our prototype, our third prototype. This is the one that is currently running. If you go on our website and you click on Mauna Loa on units, Mauna Loa system, you will actually find live image of the webcams that are monitoring this unit, and you will find the 100th image that was taken the previous night, so as a sample image of what this unit acquires. And the goal here was to compare our original choice of lens, which is a $2,000 lens, very high-end Canon lens, f1.2, with a much cheaper alternative, which is f1.4 85mm lens, manual, and which costs significantly less, actually less than $300. The conclusion is that the cheaper lens is actually quite good and almost as good as the much more expensive lens, and that's the one we're going to adopt for the baseline to keep the cost small. And we also demonstrated that an extension to the baseline is quite feasible to have 4 cameras on the same mount. So the type of mounts we're using, which is typical amateur astronomy, between $1,000 and $2,000 mount, is well capable of supporting 4 cameras. Next slide 26, shows that what we started doing also is improving the electronics, streamlining it, using more standard components to move in the direction of establishing a baseline, something that's more reliable, easy to duplicate by others. And Josh will talk more about this ongoing effort. Slide 27 shows an example image with the lens for the baseline, which is 85mm f1.4 lens. And on the top left, you can see a full frame image. And there's a small box which shows the area that is zoomed on the rest of this slide. So the big image is actually a zoom on the lower left of the full frame. And you can see that the image quality is actually quite outstanding, even on a lens that costs less than $300. So I will now hand the presentation over to Josh, who's going to talk about the baseline unit.
Thanks, Ollie. So as Ollie said, I want to talk a little bit about the baseline unit, which is where we're going now that we've tested things out with the prototypes. But before I get into that, I just wanted to point out a couple of things. One, all of the prototypes that Ollie has talked about so far have basically been his work on the weekends. This is, a hobbyist building this on the weekends. This wasn't some big funded project by the NSF. This is really amateur science. And after seeing how well they performed, we think that there is real potential here, which is why we're building this PANOPTES project and why we're trying to recruit more people to build units like this. So in order to make that happen, we're going to build this baseline unit. And the idea of the baseline is it's a new design using everything we've learned from the prototypes, and it'll be one which we will be documenting on the website, and it'll be sort of a common point of reference for all the future evolution. So different people can take it and evolve it and change this or use a different mount or try different cameras and lenses, whatever they might want to do, but the baseline is sort of that common point of reference. And so what I want to describe is how we see this project moving forward from today, because basically we've got this prototype up and now we want to build this baseline. So we're hoping over the next few months to build the first baseline unit and document it and put that on the web page. And so what happens after that? How do we build this community? So that's the phase 1, which I talk about on slide 28. If you look at slide 29, phase 2 is really, once that baseline is done and described, what we're hoping to do is recruit a sort of core group of users, mostly professional and amateur astronomers is what we expect, to basically build their own versions of the baseline unit and try it out, basically figure out what did we do wrong, how can we improve this, and basically get a community discussion going about the baseline unit and how it works and how it should evolve. And so these users are what we consider expert users, people who come in with at least a little bit of knowledge about astronomy, mounts, astrophotography, whatever it might be. Once we have that sort of core group of expert users, we then move on to phase 3, which is on the next slide, where we begin to actively recruit a much, much larger pool of users. And we're very interested in getting schools involved, because we think that building a unit, a PANOPTES unit, makes for a very interesting and very exciting project for high school, middle school, schools, and students, because it involves a little bit of programming if they want to try and modify things. It involves electronics, things that are involved in robotics, which is a big thing, at least here in Hawaii. We're seeing a lot of schools doing robotics projects. And so, but one of the key things that we're going to run into is if we've got a lot of schools, and we're not expecting the students and the teachers to necessarily come in with as much knowledge about astronomy and astrophotography as some of the amateur or professional astronomers that we recruited in Phase 2, if it's just me and Ollie and half a dozen other people in sort of our core PANOPTES group, we're not going to be able to keep up with people's questions, with requests for help. And that's why we want that sort of core group from Phase 2. And basically this becomes the user community, where everybody's helping one another to build this, and especially helping out new users, people who are coming to this who have an interest but maybe not as much experience. And so that's really going to be where PANOPTES succeeds or fails, is do we successfully build this user community? Because if we do that, then it'll take off and gain its own momentum. Whereas again, if it's just 3 or 4 of us trying to answer all the questions, it's going to be really tough. So we're really interested in getting a bunch of core users, and that's where you guys come in. If we look at the next slide, what makes the baseline different than some of the prototypes that Ollie described? And so, our goals in building this baseline unit really come down to how simple can we make this. And I've worked on other robotic telescopes in the past, and a good sort of core principle to embrace is keep it simple. Simple systems tend to be very reliable. They have fewer things to break, less things to go wrong. The other thing is that simple systems are easier for other people to build and understand and improve upon, which is core to how we want PANOPTES to evolve. And every time I give a talk about hardware for robotic systems, I have to throw in this quote because I think it really is a good guideline for how people should look at the design of systems like this. And it is, perfection is finally attained, not when there is no longer anything to add, but when there is no longer anything to take away. So again, keep it simple, and that will be much more reliable. So we go to the next slide. One of the things we're doing is in the prototype, we use some custom digital input-output and analog input-output boards to handle sensing the weather, sensing limit switches for the mount, things like that. Well, what we want to do is not get tied into particular external boards. And so what we want to do is use Arduino prototyping platform. And for those of you who are not familiar, I put this quote that I pulled off the Arduino webpage. And what it says is, Arduino is an open-source electronics prototyping platform based upon flexible, easy-to-use hardware and software. And here's the key. It's intended for artists, designers, hobbyists, and anyone interested in creating interactive objects or environments. So the key is, you don't have to be a programmer or an electrical engineer to use this. And so as an example of that, on the next slide, this is actually a diagram that was put together by an undergraduate student who worked with me for a few weeks this past summer. And this student was visiting Hawaii and working at our planetarium, but she wanted to do a small project working with one of the observatories. And so she only had a few weeks, and she got interested in PANOPTES, and so we decided that what she should do is basically write the code for this Arduino board to read a whole bunch of sensors that would basically together add up to being a weather station. And she came in with zero experience in electronics and very little experience in programming, and in about 2.5 weeks was able to assemble the circuit that you see here, this is her diagram, and then write the code that ran this. And this code, if you look carefully at this diagram, one of those LEDs was basically giving you a safe or unsafe signal that said either, it's raining, or it's very humid, or it's very, or it's very cloudy, and it would tell you whether or not it was safe to operate your telescope. And all of this happened within that little Arduino board, which is, again, fits in the palm of your hand. So this is something that should be fairly easy for most people to just do a little bit of, background research, and then they can get their hands on it and actually start making changes and improvements. So if we look at the next slide, one of the features that we're going to try and add to the baseline unit is something we've debated a lot, but one of the difficult things with erotic telescopes is safety. You don't want the telescope physically crashing into things. And so if you look at really high-end telescope mounts, I mean a Paramount or an astrophysics, they have limit switches built into the mount or homing switches built into the mount. But because we're trying to make PANOPTES accessible and at a cost where schools and individuals can build it, we don't want to have a $10,000 mount be the basis for our design. So what we're going to try and do is get that same feature, but without actually modifying the mount. You don't have to build custom mounting brackets to put limit switches and home switches on the mount. So what we're going to do is use an accelerometer. And what this idea is at its root is that you look at a smartphone, and a smartphone knows how it's oriented. It knows which way is up and down. So why shouldn't your telescope? So we're hoping that by putting one of these accelerometers, or technically we can use another device called an IMU, an inertial measurement unit, in the box that holds the camera, and you read that information from that accelerometer with the Arduino board, it'll tell you what the orientation is. Now, it's not as accurate as the encoders on the mount, but what it means is that you can never get truly lost with the mount. You can always figure out which way you're pointing. And so by using this, we're hoping to avoid using limit switches, home switches, or absolute encoders, which are either very expensive or require you to physically go in and modify the mount to get them. So this is something we're testing out. We're not 100% sure it works yet, but we think it will, and I'm kind of excited to see how this does. If we go to the next slide, I just wanted to give you this quick overview of what we sort of envision the baseline unit being. We're going to take all the electronics, the computers, the power supplies, and just store them in a weatherproof box. In this case, I think we're just going to use a commercial Pelican case. Some of you may be familiar with that. And once you build this case, basically you've just got power going in and then a few cables going out to the mountain cameras. And all of the sort of complicated stuff is stored within this case. Then you connect those up to your mount, and then we're going to build a similar case that just holds the cameras and whatever little electronics needs to be in and around the cameras to trigger their shutters and whatnot. So basically you end up with a modular system. You have three things. You've got your camera box, your electronics box, and your mount. And that's an entire PANOPTES unit in these three modules. And so, again, we're trying to keep this relatively simple. Once you sort of have each of these three modules built, it's really simple to understand what's going on with each of them. So that's what we're hoping to do with the baseline unit. We're hoping to have that done sometime within the next 3 to 4 months. We'll see, how well that does with that estimate. Always seems to take a little bit longer than we expect, but certainly early next year to have our baseline unit published. And so with that, I'm going to hand it over for just a few minutes to Mike to talk a little bit about software.
Thanks, Josh. Well, Josh talked about the hardware that we're going to use to construct the baseline unit. I'm going to chat briefly about the software that's going to control the system and going to ultimately process the data that we take from all the participants' units. We're going to build software that will robotically control the PANOPTES unit. This has already been tested on the baseline unit, but we're going to expand the software and modularize it so that we can accept additional hardware that hasn't already been incorporated. We want to be flexible and allow people to change the software. Our plan is to ultimately create an open source control system that's going to be accessible to anyone who wants to participate in the PANOPTES project. The software itself is going to be relatively simple. It's going to do the minimum necessary to control the mount, accept a schedule, take data, manage the data, monitor the weather, and protect the mount, provide a basic user interface so that participants can control the telescope, and then report the results. Olivier talked a little bit about the algorithm that we're going to use to process the data for a single image. That brings us into a nice discussion of how much data we're going to actually capture. We're going to capture lots of images, almost 300 gigabytes of data per month for a two-camera PANOPTES unit. That's a lot of data. It's too much to be sent over the internet easily, so we have to plan to retrieve the data every couple of months by exchanging hard drives. Processing that data is going to be a real challenge, and we're going to have to look at cloud computing type concepts, maybe a SETI-at-home style distributed data processing technique, and there's going to be a lot of opportunity for people to get involved in the data processing side. Since this is ultimately an outreach program, we're looking at ways for people to participate and to help expand both the software for the unit and the data processing software. The baseline unit software is going to be open source and made available on GitHub or something similar so that anyone who wants to participate can easily download, use, and modify and improve the software. And with that, I'm going to go ahead and turn the conversation back over to Olivier.
Thank you, Mike. And so we're now on the last slide, slide 36. I think the most important question hopefully for many of you is how do I participate to this project? Reminding everyone that participation is wide open to all, and we encourage participation at any level. There are many ways you can participate. You can write code, help us figure out how to build a baseline, build a unit, process data, improve the hardware, start a new type of hardware. You can, if you have a telescope that's quite capable, you can actually follow up interesting targets that we're going to find with those small cameras. You can also provide data storage. So there's many ways you can participate. What I encourage you to do is to email us at info@projectpanoptes.org. If you want to join, drop us an email. We'll include you in the Google groups that we have, and you'll see the trail of emails that is going back and forth, mostly on the baseline right now. And another way you can help, of course, is to help us advertise the project and make it widely known among the amateur astronomy community. Thank you very much.